Yeah, I think it's been some time we met, so I hope at least many of you remember what we discussed in the last class. So we were discussing about virtual memory. Specifically, do you remember what we discussed in the last class with respect to virtual memory? What exactly did we discuss? Okay, so I'm not getting any responses. So okay, so we talked about page table, and with respect to page table, we talked about fast address translation. Okay, so again, normally when we have a page table, again, this is the example that I gave. So we have some program where you'll have some virtual addresses which are mapped to some of the physical addresses that are there in the main memory. And now typically page table will be available in the main memory where you will have some entries and you'll have a valid bit which will indicate whether that particular page is available in the main memory or not, and then you will have a mapping information. So these are all valid mapping information which will tell you where exactly the pages are located. Okay. So now whenever the processor requests for some address access, it has to access main memory twice. Okay. So one is to access the page table to get the address mapping information from which you will be able to translate the virtual address to physical address. Then you will get the physical address, right? Then again you access the memory second time to get the data from that physical address. Okay, so you'll be accessing the main memory twice, once to get the address, the second time to get the data in that particular address. So this is a very inefficient way. So that's why, again, you know that the page table will be mapped based on the information that is there in the page table register. Okay. Now, for example, in this case, if you are trying to access a virtual page 0, it will get translated to physical address 3 and you will be able to access the page. So this is the case of page hit. Now, if you are able to, if you are trying to access, let's say 3, virtual page 3, but the valid bit corresponding to that is 0, that indicates that the page is not available in the main memory, then we have to fetch that corresponding page from your secondary memory. So this is an example of a page fault. Okay, so which is a very rare occurrence, but it still occurs. Okay, so now to avoid accessing the main memory twice, you have a small memory which behaves very similar to cache, which you put closer to the processor. It will have limited number of entries than the actual page table. So here, let's say you have only 2 entries. So in this case, when I try to access virtual page 1, okay, so it will be a TLB hit because I am able to find the translation information in the TLB only. Okay, so and if I try to access, let's say 2, so this information is not available in the TLB. In that case, I have to, it's a TLB miss. So it could be either a simple TLB miss or it could lead to a page fault, but that we'll be able to know only when we access the page table. So when there is a miss in the TLB, it will go and access the page table. So when it accesses the page table, then if you are able to find the translation information corresponding to that page, then you'll be getting the translation information, and based on that, you'll be accessing the main memory. But in some cases, it will be a TLB miss and a page fault. For example, if you're trying to access page 3, here it is not there, the entry is not there. And then again, if you access the page table, the valid bit corresponding to that entry is 0, which indicates that the page is not available in the main memory. So it results in a TLB miss and a page fault. Okay? So in that case, again, you have to get that page, update your page table and update your TLB also. So TLB also keeps getting updated regularly based on the which page is accessed recently. Okay, it's very similar to cache. Okay, the behavior of TLB is very similar to cache. The only difference lies in what is stored. Okay, so in the case of cache, you are actually storing the data. Okay, in the case of TLB, you are storing the mapping information. Okay, you are storing the physical page numbers related to the corresponding virtual page numbers. Okay, so that's the difference. So here you will be storing directly the data in the cache. So in case of TLB, you will be storing, you can say, part of addresses I'm storing, because this is not a complete address. This is only partial address. This is only gives you a physical page number, not the entire address, right? So you still use the offset bits to create an entire address. Okay, so it will give you partial address with which you'll be able to calculate the full address, and then you'll be able to access the data from the main. Now, till this point, the discussion was the processor is requesting for some data. The processor is sending the virtual address to the TLB. And assuming it is a TLB hit, meaning the translation information is available in the TLB, you will get a physical address. We are assuming that the physical address is directly sent to the main memory for accessing the data. But remember that we have one more element which is there in between. Okay, so normally we don't send physical address directly to the main memory. Instead, we will be sending the physical address to cache, where we'll see if the data corresponding to this address is available or not. Okay, if it is available, you directly access the cache. If it is not available in the cache, only then you access the main memory. So there are multiple elements that are communicating with each other. So how exactly this happens? What are the different possible cases that will occur? So that is our main discussion topic in today's class. Okay. Any doubts till this point? So I think somebody had a doubt at this point. TLB is only accessed when a cache miss occurred. No, 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 no. TLB, why will it access if a cache miss occurs? No, remember the initial thing that we are trying to do is converting a virtual address to physical address. Okay, we are trying to, as part of the first step, we are trying to convert virtual address to physical address. So initially, how did we do that? We said there is a table called as page table where you will have mapping of virtual to physical addresses. We'll go and access this, but this is there in the main memory. Now we want to reduce the access to main memory. So that is why part of the page table, we are keeping it in the TLB. So TLB contains part of the page table. Now, when I'm trying to convert virtual to physical address, I can access TLB and see if the translation information is available. So if the translation information is available, at this point, I'll get physical address. I still haven't got the data. It's just a physical address that I'm getting with the help of TLB. Or for that matter, after accessing the page table, I'm getting the physical address. I need to still get access data. So where is the data there? So once I get the physical address, then I'll access the cache to see if the data is present or not. At this point, there might be a cache miss, cache hit, all of those cases. Okay, is that clear? So the first access that is done is for converting your virtual address to physical address. See if there is a TLB. So first you check if there is a translation information available in the TLB. If it is not there in the TLB, then you access the page table. But after all of this, what do you get? You get the address. You still haven't got the data. To get the data, you access cache. Okay, so if the data is available in the cache, fine. If the data is not available in the cache, then you go access main memory to get the data. Okay, so this will become when I show exactly how the interaction happens. So normally you'll get the virtual address when the processor is accessing the memory. It will send the virtual address. Now the virtual address can be divided into a virtual page number and a page offset. Now with this, what will you access? With this, you will be accessing a TLB. Okay, the translation look aside buffer, where you will have more recently with the help of this virtual page number, you will access this TLB, and then if the translation information is available in the TLB, then you will get something called as, then you can say that it is a TLB hit. Once you access the TLB, you will get the physical page number. Okay, so we are only dealing with page numbers because that's how the entire program gets divided into. Okay, and you attach the same offset, and then that is how you will be able to get the physical address. Okay, so with the help of virtual page number, you will be able to get the physical page number. Why is the dirty bit? Again, that I have already explained, right? So why is the dirty bit here? Why is the dirty bit again? TLB is like part of PTE, okay, page table. So page table will have this dirty bit information. So can you tell me why is this dirty bit required? Other people, again, if you have understood, why is this dirty bit required? See, since what I told you is we are talking about memory accesses, right? So let's say there is a processor and you have your main memory and you have your page table, okay, somewhere. And let's say this is the page that I'm accessing. Okay, so let's say there is a page that is getting accessed. It is requesting some address information, let's say X. and we say that X is mapped to A. And this processor is writing some data into this location. Okay, so this location, and again, let's say this is the address. So XY is the address total. Then let's assume that X bits represent the page number and Y bits represent the offset. In that case, X translates to A, and the address will translate to AY, let's say. Okay. Now, if you are writing some data here, okay, if you want to write some data here, the data will get updated only in the main memory. Okay, it will not get updated in the actual hard disk. Okay, it will not get updated here. It will only get updated in the main memory. Then you need a way to indicate that it has been updated only in the main memory, right? So that is indicated with the help of a dirty bit. So for that translation, so for this translation X to A, you have a dirty bit. You make that one, indicating that for this page, you have altered this page by writing something into it, but you have modified only the main memory. Okay, you have not modified the corresponding information in the hard disk. So that is indicated with the help of dirty bit. Okay. Okay, so once you pass the physical virtual page number to the TLB, you will get the physical page number. You use the same offset bits to get the complete address. Now you know how this physical address gets divided, right? How this physical address gets divided. For this we go back to our cache basics. So how will this physical address gets divided? You should tell me. How will the physical address gets divided? If you want to access the cache, and if I give you some address, what will you do with that address? So you divide. Basically, you divide it into different fields. What are the different fields? You divide it into tag field, you divide it into index field, then we divide it into block offset field. Okay, so this same address gets divided into different things. Okay, so initial part will be tag on the MSB side, then you will have index, and after that you will have block offset. Of course, depending on your word size, some bits you might be neglecting. So this physical address will get translated into all of these bits. You partition this physical address into different fields, and then you use. Okay, so you'll use the index to access the cache. Okay, and from there you will get the tag that is already stored. So you compare the tag with the incoming tag. So this will tell you whether it is a hit or a miss. Again, a valid bit also will help you to indicate whether it is hit or a miss. And after that, you will get the data. Okay, so of course you'll get many data, and the block offset will help you to choose the correct data, and that will be sent to the processor. Okay, so this is how your TLB interacts with cache. Okay, so this is how your TLB interacts with the cache. But again, there are much more complex things involved here. So this is a best case scenario. Okay, best case scenario is you are able to find the translation information in the TLB, and you are able to find the data that you are looking for in the cache itself. So it's basically a best case scenario of TLB hit and a cache hit. This is the best case scenario that I'm talking about. Okay. Now, if there is a TLB miss, what happens? You'll not get the translation information from here. So where do I get the translation information if it is a TLB miss? If it is a TLB miss, where will you get the translation information? You have to go for to PT, and there again you have to check the valid bit to know whether it is the page is there or not. Okay, so we'll try to analyze different scenarios. Okay, so and maybe we'll also predict the approximate number of clock cycles that will be required for each case. Okay. So we'll try to analyze with the help of this visual representation. Initially, the processor will send a virtual address, and that virtual address will be sent to TLB for getting the address translation information. So from there, you'll get the physical address. Okay, so if it is a TLB hit, you will be able to get the information in the TLB itself. So this is like virtual address that you'll be sending, and you'll get physical address. Okay, and this physical address you will use to access cache. And if at all, if you are able to find the data related to this address, then it will be a cache hit, and you send the data back to the processor. Okay, so this is the best case scenario that will occur. Okay, and most of the times you will be encountering this only. Okay, most of the times, if you reuse the instructions and reuse the data more and more often, this is the scenario that you will encounter more frequently. Now, what will be the typical number of clock cycles that might be required here? Can you take a guess? Can you approximate typical number of clock cycles? Is it always one? Or is it always two? It depends on implementation. Is max is two. Okay, if you say that TLB access will require one clock cycle and cache access will take one clock cycle, then the maximum will be two. But the range will be 1 to 2, because sometimes the way that this interaction is designed, the access, you'll be able to send the virtual address and get the data in a single clock cycle. That's a more ideal case. Okay, so if you want to design this, the TLB access should happen in a half a clock cycle, and the cache access should happen in another half clock cycle. Okay, so the range is 1 to 2 clock cycles. Okay. So based on that, you will either end up with 1 clock cycle or 2 clock cycles. So this is the best case scenario. Now, can you tell me what is the next case scenario? So this is one scenario where you will find TLB hit and a cache hit. Now let's talk about another case. So now let's say the virtual address is sent by the processor to the TLB, and here it will be a TLB hit. Okay. So TLB hit will happen, and then you will get the physical address. Then you get the physical address. So why do I say this is the next most frequently? I am also talking about in terms of what is more frequently occurring case. So I said that this is the case that will occur more frequently, and this is the next more frequent case. Can you tell me why am I saying this as the next more frequent case? Then physical address will occur, physical address will be sent to the cache, but here you will see a cache miss. Okay, so we have discussed, right? So we said that TLB miss rate was how much? If you have remember the last classes, we said the TLB miss rate is 0.012, somewhere around 0.1%. Okay, whereas your cache miss rates was how much? Cache miss rate typically was somewhere around approximately 10%. So you see that you have this occurring very rarely, the TLB miss occurring very rarely. Okay, and cache miss occurring more frequently than TLB miss rate. We have discussed about the reasoning for that also. Can you tell me what was the reason for that? What was the reason for TLB miss rate to be on much lower side when compared to cache miss rate? Because of the large page size. Yeah, exactly. Okay, so the TLB has page information, page translation information, and a page is a bigger block. It will be in terms of KBs, whereas cache, the size of each block will be in terms of maybe 16 bytes or so. Okay, 16 bytes, whereas here you might have 16 kilobytes. So when you access this once, when you try to translate this information, you keep on accessing within this range only most of the times, because your instructions will be there within that, your data will be there within that. But whereas cache, so it keeps on changing, your data keeps on changing, because this 16 bytes will keep on getting replaced. So you will have more miss rate for cache when you compare it with TLB. Okay, so this we have already explained. I just covered it as an addition to this. So now that is the reason we are saying that this is the next more frequently occurring case. So a TLB hit and a cache miss. Now tell me what will happen if there is a cache miss. Now I have sent a virtual address. Okay, virtual address I have sent. I have got physical address. So what do I do with this physical address? Now it is a cache miss, right? So if there is a cache miss, what should I do? There will be some penalty incurred, that's correct. But if it is a cache miss, what should I do? I should now access the main memory. Why am I accessing the main memory? This also you should be very clear about. Why am I accessing the main memory? There are many reasons for accessing the main memory. What is the reason here? Again, whether to get the data or to get the address. So here we are accessing the main memory to get the data. Okay, so this access is done to get the data. You will get the data that will get updated in the cache, and that data will be sent back to the processor. Okay, so this is the next most frequently occurring case. So in this case, can you tell me approximately how many clock cycles will be required? Approximate. We talked about, now we have been assuming some things, right? No, not 20. Okay, maybe if you have a very good main memory, maybe 20, but it is in terms of hundreds of clock cycles. Okay, hundreds of clock cycles. Why is it hundreds of clock cycles? Because typically the main memory access will take those so much time. Okay, so equivalent to miss penalty. Okay, hundreds of clock cycles is what we have been assuming as our miss penalty case. So that is why it will require hundreds of clock cycles. Now, what is the next case? The next case. Okay, with respect to number of clock cycles. So the next case is when you have a TLB miss. Okay. So a TLB miss. So what does this TLB miss mean at this point? What do you mean by TLB miss? So what do you mean by TLB miss? So I have sent the virtual address from the processor to the TLB. So that page translation information is not available in the TLB. So if it is not available in the TLB, what should I do? I should be able to get go and access the page table. Now here I'm accessing the main memory. But again, as I said earlier, you should be clear about why am I accessing the main memory. So here I'm accessing the main memory to get the address related information, not the data, but address related information. So once you access your page table, I'll get that information. I'll again update my TLB. Some old entries will be replaced, some new entries will be put up in the TLB because this is now most recently accessed data, so that I'll update in the TLB. Now, once I get that, I'll be able to get the physical address. Okay, so now I'll get the physical address. So now physical address, I'll send it to the cache. Okay, so now cache might be a hit. The data that I'm looking for might be available in the cache. So I can send that data to the processor. Okay, so this is another case. So typical number of clock cycles here. Typical number of clock cycles in this scenario. Again, hundreds. So you are accessing the main memory again. It's like a penalty, but for TLB. So it's like hundreds of clock cycles. Okay. So this is the next scenario. Now we have discussed about cache hit, TLB hit. Okay, so we have discussed about TLB hit, cache miss, and this is the case of TLB miss and cache hit. Now the next scenario, let us say, can you take a guess what will be the next scenario? So in these cases, so let's say cache, so you have something related to TLB. So first is TLB, right? Okay, so first you have something related to TLB. Okay, and then you have something related to cache, and then there is something related to page. Okay, so initially we discussed about hit. This is not applicable because we can say it as page hit only. Okay, not applicable, but you are not talking about any page here, but you can say this is a page hit. Now the next case that I discussed about is TLB hit. This is a miss, but it's still page hit. Okay, because the information is still available in the main memory. Now, then the third case that I discussed was there's a miss here and there is a hit here. It's still a page hit, okay, because you are able to access the page table and you find the address translation information here. Okay, so these are the three cases that we have discussed. So first will end up in 1 to 2 clock cycles. The second case is hundreds of clock cycles, and the third case is also hundreds of clock cycles. Now, what will be the third scenario? The third scenario is you have a TLB miss. So you send the virtual address to TLB, but there you will find that the translation information is not available. Then you go access the page table, but you will find the translation information in the page table, and the page is also available in the main memory. So that way you will be able to get the physical address. Once you get the physical address, so that physical address you will be sending it to cache. But when you see in the cache, the data that you are looking for is not available. So it is a cache miss in this case. So when there is a cache miss, then again you have to access the main memory, but this time for the data. The first time that you accessed the main memory was to get the address information. The second time that you are accessing the memory is for the data information. So this is a case when it is a miss here, but is a hit here. Okay, the page is still there in the main memory. Okay, we are not talking about a case where the page is not available. It's still a hit, Now for this case, how many clock cycles? It's basically double the miss penalty of a cache, so it will be 200. So let's say if this is 100, then we can say it is 200 of clock cycles. Okay, twice the amount of miss penalty is typically what is required in this scenario. Okay, this is another case. Okay, so in all of these cases, we are talking about a case where the page is available in the main memory. Okay, now we'll talk about more extreme cases. Okay, so if before the TLB and cache was there, before we introduced TLB and the cache, we said this was the scenario. We were accessing the main memory twice, once for getting the address and other time for getting the data. Okay. Now, once I included TLB and cache, this becomes one of the occurrences. Okay. And then you send the data to the cache. More less frequent or sorry, less frequent occurrences when you try to access a TLB. So it will be a miss in TLB. But then when you access the page table, okay, when you access the page table, you will find that the corresponding virtual bit is 0. Okay, what does that mean? What does that mean? It's a page fault. Now, yeah, valid bit information in that page table is 0. So what does that mean? So it basically means that it is a page fault. Okay, the page is not loaded into the main memory at all. Now, when the page is not loaded into the main memory at all, okay. Now, what does that mean? What does that mean? So it's like I'm trying to access the secondary memory to get the data. Okay. Then I'll update my main memory with that. And now I'll send the translation information to TLB. Now I'll send the physical address. So this is like virtual address. Now I've got the physical address. Okay, now tell me what will happen in the cache. Do you think there is a possibility of a hit? Or do you think a cache miss will occur for sure? Can you give me justification for that? Why do you think cache miss occurs? Why do you think cache miss occurs? It's all to do with the sizes and things like that. So if you are never loaded the data into the main memory itself, okay, we say that main memory itself contains frequently used data. And you have if the particular page is not available in the main memory, then it basically means that it is not used for a very long time. And if you're talking about 8 GB memory space, and if you are saying that it is not loaded into this 8 GB memory because it is not used for a very long amount of time, then what is the probability of finding that in the cache? That's like not possible. Okay. So hence, in this scenario, whenever there is a page fault, we always end up with cache miss. So we basically say is that data cannot be allowed in the cache if the page is not there in the main memory. So if something is not there in the main memory itself, then you will not be able to find that in the cache. Okay, so this result, the page fault, will always result in a cache miss. Okay, there is no possibility of getting a cache hit. Okay, so that is again one more important point to remember with respect to this. Okay. Now, when I said that there are 3 possible cases, now at this point, what happens? So at this point, again, I have to go access my main memory, get the data, update my cache, and then only I'll be able to send the data to the cache. Okay, so here I'm accessing main memory twice, okay, and your secondary memory once. So here, typically, how many clock cycles will be required? So we talked about 1 to 2 clock cycles. We talked about 100 clock cycles, 2 cases. Then we talked about 200 clock cycles, twice this amount as one case. Here it will require millions of clock cycles because of this, okay? Because of this being a page fault. So now the reason that it will take millions of clock cycles is many. One is the access time for your hard disk, your secondary memory. The other thing is OS gets involved. So there are a lot of time spent in doing a lot of things. Okay. Yeah, there is also a possibility that there is no mapping that exists. Mapping where? So no mapping is meaning the valid bit is 0 in the page table, but that basically means the page is not there. So once you get the page table gets updated with the mapping information. That mapping information will be updated in the TLB also. Okay. No, never. A TLB hit and a page fault cannot occur. That's the same thing, right? So it's very similar to cache only. So if you are able to find the if you say that it is a TLB hit, then definitely that should be available in the cache. Okay, so there is no case of TLB hit and a page fault because the valid bit will be 0 here also. The valid bit to the corresponding information will be 0 here also. It basically means that that particular page is not available. Okay, in the main memory. So TLB hit and a page fault will never occur. So can you tell me now what all cases will not occur? So these are all the possible cases that will occur. So this is a TLB hit, cache hit. This is a TLB hit, cache miss. This is a TLB miss, but cache hit. This is a TLB miss, cache miss. For all of these cases, it is still a page hit. Okay, and only for this case, it's a page fault. Okay, page fault. Now, what are the cases that never occurs? Can you list all of those cases which will never occur? And can you give justification for those? So this is like we talked about cases. So one is TLB miss, cache hit, and page fault will never occur because when I say page fault, the cache cannot be hit. Okay, and then TLB hit, cache miss, page fault will never occur. There is no possibility of TLB hit with page not being present in the main memory. A similar version, TLB hit, cache hit, and page fault will never occur. So once I say TLB hit, it cannot coexist with page fault. So if it is page fault, then there is no possibility of page hit happening, either as a cache miss or a cache hit. Okay, so these are the three cases which will never occur. Okay, so there are only three different things. So TLB and cache and page. So there will be 8 possible cases. So out of this 8 possible cases, we have discussed about 5, and these 3 are the cases which will never occur. Okay, so this is all about the interaction between the uh, processor, cache, the TLB, cache, and the main memory and the secondary memory. Okay, so now this is all of the case where the processor is sending virtual address, which which is used to get the address information, physical address information from the TLB, and then there is a cache involvement, right? Now there is this extra access that is being done to the TLB. So some people, what they say is, why don't I avoid this? Why don't I use virtual address directly to access the cache? Now, in this case, the cache will contain the virtual addresses. They will not contain the physical addresses. Later, I'll include TLB. Can you tell me what is the advantage of having this? What is the advantage of having this scenario? I'll send directly virtual addresses to the cache. And then if at all I want to access main memory, then only I'll use TLB. So what is the advantage of this? You save time for translation. Okay, so because you are not doing translation, if it is a cache hit, okay, if the data that you're looking for is available in the cache itself, the interaction will happen between the processor and cache only. So that's like if earlier case you were taking 2 clock cycles, now you'll be taking only 1 clock cycle because you are accessing directly the cache. Okay, so that is another scenario where the cache uses the yeah, so if the other interaction is you need to translate before cache lookup. The other alternative is to use virtual address itself to access the cache. So the advantages I told you about. So you don't have to access TLB. So you can directly access cache and identify whether it is a hit or a miss. Based on if it is a hit, you do the normal process. If it is a miss, it's very similar to other cases. But can you tell me what will be the disadvantage? What will be the disadvantage? Any idea? Cache miss would be costlier. Um, you can't say that, no? It's very similar to earlier case. If at all there is a cache miss, you go to TLB. TLB might be a hit. So it's like other scenario only. It's more or less other scenarios will repeat. Multiple programs, we would have to empty cache. That is as good as that is being done now. When there is a context switch from one program to another program, okay, so there is always you have to make your valid bits of your cache as 0 only. That is as good as emptying cache. You have to do that in the other case also. Any other answers for this? So there'll be some complications due to aliasing. Okay, so what do you mean by aliasing is different virtual addresses will may be pointing to a shared physical address. Okay, I'll explain about this. Okay, a little bit in detail. Okay, so it basically says even though the physical address is same, there might be a false miss in the cache due to different virtual addresses. So what exactly it means? So let's assume that in the main memory, okay, in the main memory, we are talking about the same, maybe same program or different programs sharing the same memory. Okay, so let's say there is this program, there is some location in your main memory, which is corresponding to a physical address A. Now, when you are accessing cache with the help of a processor, you will be sending virtual addresses. So let's say the virtual address is X. Now you will be checking for X here. Okay, let's assume that initially it is a miss and later you fetch the data and the data related to X is now available in the cache. Okay, now if at all there is another program that may be using the same location, the virtual address in that case is, let's say, Y. Okay, so some program is using a virtual address Y, but since the memory is shared, the X and Y are mapping to the same physical address. Okay, because it's shared between two programs. It's the same physical address is pointed by two virtual addresses. Now, whenever I'm trying to access, let's say A contains some 22 data, and when you access the location X, if at all it was a miss, so you got 22 here. Now, whenever I am sending the access address as Y, what will the cache see? What will the cache say? Will it say it as a hit or will it say it as a miss? Will it say that there is a cache hit or a miss? So it will say a miss. Why will it be a miss? Because the addresses are different. So the tags will not match. The tag with respect to this address will not match with the tag that is stored in the cache. Okay, so the tag for this Y address will not match. So it will show it as a miss. But is it actually a miss? Is it actually a miss? No. Why is it not a miss? This is a false miss. So that's why I'm talking about here, right? False miss in the cache due to different virtual addresses being mapped to same physical address. So here there are two different virtual addresses, X and Y, which are mapped to the same physical address A. So, but when once the cache sees it, okay, it will see it as a miss. Okay, but that will not happen in the case of physical address. So because the translation will be done before. So because whenever you try to send X to TLB, it will give you A, and in the cache you will have A related information. It will have 22. When I send Y to TLB, it will still again give an A. So here in this case, it will be a hit because the location A data is already available in the cache. But here, since I'm dealing with virtual addresses, I'll see these two addresses as different, but they are mapped to the same physical address. So that is what we call it as aliasing. Okay, in the case of using virtual addresses, so different virtual addresses are using the same physical address, due to which you will face false misses. Okay, this is one issue that might occur. So a miss is a miss. Okay, so when there is a miss, there is a penalty involved. So when you encounter this false miss unnecessarily, you are wasting clock cycles. So that's like a disadvantage. But again, on the flip side, there is some advantage in the sense you don't have to go through the TLB every time there is a cache hit. So whenever there is a cache hit, you will get an advantage. Okay. So this is one example. They still use it in some cases. The likelihood of this happening is limited. Yes, of course, the likelihood of two virtual addresses mapping to same physical address is limited, but unnecessarily you will end up seeing false misses. So both the techniques are used. Okay, it's not that one technique is preferred over the other based on how your program is. Okay, based on how accesses are being done. So both of these are preferred. Okay, so I explained about both of these cases. Only thing is, in the case of virtual address tag, you remove the TLB. Okay, so TLB access will be done only later. Only if there is a cache miss, then you will access the TLB to see if the translation information is available or not, and then so on. Okay, there will be slight change in the what you say configuration. So in the earlier case, okay, so if I want to show, the configuration for this. So there will be a processor. So you will send virtual address. Okay, so it will access cache. So if there is a cache hit, you don't worry, you send data directly. Okay, this is the best case scenario. If at all there is a cache miss, now the first thing that you do is again you access TLB. So here there are two possibilities. So it's a TLB miss or if there is a TLB miss, again you access page table to get the translation information. And then again you access your main memory to get the data and so on. Okay, so your main memory, okay, let me put it in a proper way. So in this case, let's talk about TLB hit. So if it is a TLB hit, what happens? So what will happen if it is a TLB hit? Can you tell me in this case? So if this is your main memory, so if it is a TLB hit, what will happen in this scenario? So I've sent the virtual address to cache. If it is a hit, you send the data to the processor. If it is a miss, then you send the virtual address, okay, to the TLB, and you found that it is a TLB hit. So once your TLB hit, do you send the data directly to the processor? No, because it is a cache miss, you still have to access your main memory to get the data, and that data will be updated in the cache. Okay, and that data will then be sent to the processor. Okay, this is next case scenario. And what happens if it is a TLB miss? What happens if it is a TLB miss? Again, you have to access your main memory, but now to access the page table, then again you have to get the translation information, and then you have to again access the main memory to get the data, update the data, and so on. Okay, so this is how it will happen. And the last case will not occur. The last case is the cache, again, the cache miss, TLB miss, and the page fault. Again, it will occur. So page fault case, you know what happens. You have to fetch that block from your secondary memory, put it in the main memory, and so on. Okay. So this is how the interaction will happen if at all you are dealing with virtual addresses. Okay. The cache is dealing with virtual addresses. Okay. Yeah. So there is one more small point that we talk about is with respect to involvement of OS. So here we have abstracted a lot of things. Okay. So we are saying that if it is a page fault, you bring a page from your secondary memory and put it in the main memory. It's not as simple as that. Okay. So there is a lot of OS involvement also there. Okay. So there is some kind of protection required with the help of assistance because multiple programs might be running. Okay, so you might have to protect memory access against errant accesses, which will be requiring OS assistance, and you will require some OS hardware support for this also. Okay, so OS to handle OS related operations, you will have in the processor you will have something called as privileged mode or kernel mode. Okay, and you'll have a dedicated instructions for that mode. Okay, your user program will not be able to access these instructions. Only your OS will be able to use these instructions to modify a few things. Okay, so it's like page tables are stored, other information, all of this information is available only in the supervisor mode. So if at all you take up the OS course, then many of these things you'll be able to be able to identify. Okay, so what exactly happens whenever there is a page fault? Okay, so it's not that hardware does everything. It's like OS takes ownership of the processor. The processor will start executing OS related instructions. So a lot of things happen there. Okay. So with respect to that, again, it's out of scope for this course. So if somebody is interested to learn these topics, you can go through some OS textbook and find out exactly what happens. Even there, the explanation is very minimal unless you experiment, unless you do some maybe some exercises or experiments with respect to OS. Only then things will clear. If you see the textbook, the same explanation is given. The same explanation that I gave you. Okay, only thing here is we in the main memory we say that we are loading a page. They call the space to load a page as a frame. That's the only difference you'll find with respect to the explanation. But what exactly happens with respect to OS? So those things I think you have to go a little more in depth. Maybe advanced OS. I'm not sure. Okay. Okay, I think with this we have completed our memory organization topics. So initially we discussed about cache, and then we discussed about virtual memory. There is one problem related to this virtual memory. Um, Again, it can maybe we have some time we can finish this off. So we are saying that virtual memory uses a page table to track the mapping of virtual to physical addresses. So this exercise basically shows you how this table must be updated. The following table is a stream of virtual addresses as seen on the system. Okay, so we'll assume that the page size is 4 KB, uh, and we'll assume that there is a 4 entry TLB. I mean, TLB has only 4 entries, which will follow true LRU replacement. So whenever you want to replace some entry, there you will follow accurate LRU. Okay, the mapping information if you want to replace, there you will follow accurate LRU. And there is some additional information because we don't know how the OS does things. To mimic the behavior of OS is very difficult because it uses some complex algorithms. So we'll do one small approximation here or small assumption here. So whenever the pages are brought from the disk, okay, whenever something is brought from the disk, okay, we'll give them the next largest unused page number. I'll explain it as we go through this problem. Okay. If at all we are trying to bring a particular page and we are trying to put it in the main memory, we'll give information such that the largest page number, unused page number, will be assigned to it. In this case, we are trying to assume that the main memory is very large. It will have a lot more information. So based on that, we are trying to implement this. Okay, so these are the addresses that are being accessed. Okay, 4669, 227. So all of these are the addresses. So first thing, what do you do with this? And again, other information is also given to you. So this is the current page table information. So you see that one of the valid bits is 0. That indicates that this information is invalid, and you'll not be able to find the translation for virtual page number 4. And also you'll not find the page related to this in the main memory. So that is what it means. And you might have some page table like this that is loaded in your main memory. And for all of these cases, we are assuming that the data is not available in the main memory, and we are supposed to bring this data and put it in your main memory. Okay. And then you have to allocate some mapping information. So this is where I'm talking about. So if at all I'm accessing a virtual page 1, and you see that it is there in the disk, then OS takes over and it will bring that page into the main memory and allocates some mapping information here. Because we don't exactly have an idea about what algorithms are used. So here, what will I do is I'll just assign the next highest integer. So here, what is the highest integer that is getting used in this table, in the page table? In the page table, what is the highest integer that is getting used? 12. Okay, so you have this 12 also, right? So what I'll do, I'll just say that whenever I bring a page in the main memory, it will sit in 13th place. Okay, because of limitation with how OS behaves and what sort of algorithms they use. So we are trying to avoid that, and we are trying to say that the allocation will be done in such a way that it will be allocated to the next highest integer, and we'll change this value to 1. So that's the only thing that we are trying to do something different. Okay, so given the address tree and shown the initial table state of TLB and the page table, you have to determine for each case the virtual page number, whether that will result in a TLB hit or a miss, whether it will result in a page fault, and the status of TLB after each access. Okay, so after each access, how your TLB changes, that is also required. Okay, so this is the current page table information before you start execution. And this is your TLB information before you start execution. And these are the addresses that you are trying to access. Okay. So these are some random addresses. So normally the processor might not behave like this, because if you see the page numbers will be very different. Normally the processor will tend to use the same page for multiple cycles. But here, just to understand the concept, we are giving you some addresses which are very much different. The page numbers for each of them will be different. Okay. So now I'm indicating the initial state, so the TLB status here. We can go back and always check what is the TLB containing. So the first thing is you have to convert this into hexadecimal for easier representation. Now tell me, how do I divide this address? So what will indicate page number here? By 1, 2, 3, D, H is the hexadecimal number. So how do I identify what bits will indicate the page number and what bits will indicate the page offset? So that, where do I get that information? I'll just again show the question. So this is the question that was given to you. So there are many things here. So first thing is we have the page size to be 4 kilobytes. What does it mean? If the page size is 4 kilobytes, what will be the number of offset bits? The number of offset bits will be equal to 12. Okay, because we are always assume the byte addressable memory. Sorry, byte addressable memory. You will have 12 bits as page offset. Okay, and the remaining bits will be page number. So 12 bits. Remember this, 12 bits as your page offset. Okay, so now if I'm trying to access the first address, so what will be the page number here? If this is the decimal hexadecimal equivalent of this number, so the 2, 3D will represent page offset. So what will be the page number? And for that page number, can you tell me whether it is a TLB hit or not? So for that, you have to see the current TLB status. So do you have a virtual page number corresponding to 1 anywhere here? No. So what will it tell you? If the virtual page number is not there, it will be a TLB miss. Now, how do I know whether it is a page hit or a page fault? So for that, I have to check this table. So here, the corresponding virtual page 1 has a valid bit to be equal to 0. So what will this tell you? So it's a page fault. Okay. So the first access is basically the virtual page number is 1. It's a TLB miss because it is not there in the TLB, and it's also page fault because the valid bit corresponding to that is 0. Now tell me, how does my TLB change? Now the first thing is you have to update your page table. So once I access this, how will your page table change? So now once I encounter a page fault, the OS will take over, it will do a lot of things, and your page table gets updated. Now can you tell me how will I update my page table? I'll first change this to 1, and instead of disk, okay, some random digits were there here, so that was indicated by disk. So here what will I say? Here what will I say? Again, you have to refer to the question. So what did I say in the question? Whenever there is a page miss, you read these things very carefully. So if the pages must be brought in from the disk, give them the next largest unused page number, okay, as its physical page number. Okay, so that's the reason I'll update my page table and change it to 13. Once I change it to 13, what will happen to my TLB? So this was my TLB earlier. So can you tell me how will my TLB change? Which entry should I change here? Should I change this entry, this entry, this entry, or this entry? And why? Because you have a valid bit to be equal to 0. So you always prefer to replace the entry which has a valid bit to be equal to 0. So you'll update that. So once I update that, you also have to tell me how will your LRU count change. Okay, so now the current LRU count is 2103. This was initial. Now once I update my page, so you are updating it as 1. Now the virtual page number was 1. So this entire thing gets replaced. Okay, now you are assigning it 30. So the virtual, the LRU count will change. So this entire thing gets incremented. So this becomes the most recently accessed, and this becomes your least recently accessed. Okay, so LRU is indicated in yellow and MRU is indicated in green. So this is the most recently accessed page information, and this is the least recently used access page information. So similarly, you have to keep on doing the process. The next time you tell me what should happen. So here 22227 is the 2227 is the decimal address, and this is the hexadecimal equivalent. Now I found that the page virtual page number is 0. So it is a TLB miss. So to identify whether it is a page hit or not, we'll just refer to the page table. Okay, so here, so can you tell me from this whether it will be a page hit or a page miss? It's a page hit. Why? Because the valid bit corresponding to 0th page is 1 and the corresponding physical page is 5. Okay, so that I have to update. So it's a second case, it's a TLB miss, but it is a page hit. Okay, so it's a page hit. So now important thing is how do you update my TLB status? So what will you replace now? What entry will you replace? The one with LRU3. Okay, so this is the least recently used data. So you replace this. You replace this with what? So this one will remain 1. It's a valid information. This 11 will change to what? This 11 will change to what? It is changing to 0 because that is the virtual page. And what about the physical page number? If somebody can remember, the physical page number was 5. So this, where did I get from? That I'll get from my page table. So this should be the current status. After you access this, if you see, the current status will be this. Okay, so we have 105. And at the same time, your LRU also gets updated. Now this is the most recently accessed data. So this count becomes 0, and the other things will just get incremented. So 0 becomes 1, 1 becomes 2, 2 becomes 3. So this is also showing you how exactly LRU can be implemented. So this LRU implementation is applicable for your cache concept also, because there also you use LRU, right? So this is how your LRU will work. Okay, so you need to have a 2-bit counter because there are only 4 entries, and you have to maintain the status like this. Okay, so I think with this, I hope you'll be able to do the remaining exercises, remaining address access on your own. Maybe I can show it for one more. So if I am accessing the third page, so if you see, third page is already there here, so it will be a TLB hit, and accordingly here nothing will change. Only thing is your count will get updated. Okay. Now since we have accessed this, so this becomes most recently accessed data, and the other things will get incremented. So if you see here, once I access this, so this should change to 0, and this will become 2, and this will become 1. What about 3? What about 3? Should I round it off to 0? No, it will still remain C, 3. Okay. It's like a saturation counter. Your LRU will behave like a saturation counter. And in this case, since we are accessing the data which is already available in the TLB, so only the other counts will get incremented, whereas the maximum count will remain the same. Okay, so that is like one more demonstration of how this will remain 3, whereas other counts will get incremented. Okay, so this is like another case. So I think you will be able to do, I'll upload this in the slides. You can go through one by one and see what happens. But the basic idea, I hope you have got. Okay. I think with that, I'll just end the session. Again, just to show you for the other case, it's 8. And in case of 8, it will be a TLB miss and a page fault. So you bring a new page from your secondary memory. So that's why you have been given 14 here. Page table also gets updated. And lastly, you have 11, which will be a TLB miss alone, and we have 3, which will be a TLB hit. Lastly, we'll have 12, which will be a TLB miss and a page fault. Okay, so this is one example. So you can go through. I have explained for 3 cases. The remaining cases you can go through on your own. So this is related to your assignment. I have already sent a mail related to this. Okay, so many people are getting confused whether this is a single formula. This entire thing is a single formula. This entire thing is not a single formula. Okay, so it's basically what I'm trying to say. This, the meaning of A mod 8 is A percentage 8 is what my intention was, but people have misinterpreted it. So I apologize if there was any issue with that. Okay, so you please read it as this. Okay, it's only A mod 8, B plus 2 mod 8, and C plus 3 mod 8. So that is how your X, Y, and Z of the that you have used in the instructions are found. Okay, so I just wanted to make sure that I announce this to all the students that are here, as well as those students who are not available. So I have mailed this already. I think with that, I end my session. If you have any doubts related to any of the topics that I discussed, you can clarify them now. I'm sorry again, I went over time because I wanted to complete this part. So next class onwards, we'll talk about some advanced topics related to computer architecture. So that's all from my side. Thank you. If you have any doubts, you can clarify them now. Thank you.
Sir, I had one doubt with assignment.
Yes.
Basically, like we have to implement forwarding in the second question, right?
Correct.
Like the condition for forwarding is like if the source of the uh, next instruction is the
Okay, I think I got disconnected there.
what I'm saying is like for forwarding, if the source of the current instruction is the destination of the previous
Yeah,
instruction, that is the condition,
correct,
right?
correct.
So
Yes, yes, yes.
in like real scenarios, the compiler does it, right? I mean, like
No,
it
no, no,
takes
no,
care.
no, 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 no. In real
Okay,
scenario, it can be done by compiler as well as hardware. We have shown hardware-based implementation, in the class, that you have a block, hardware
okay, I
block, which will
might
take all
have.
of that.
Okay, I might have forgotten. Okay, I mean, so yeah, basically we make a new block in the Verilog thing and then add all
Yeah,
the
yeah, yeah,
conditions.
yeah. Yes, yes, yes,
Okay,
yes. We have clearly shown how we can add a multiplexer. We have a forwarding unit which will take all of those values. Based on that, it will compute
okay.
what value to be passed. And the exact thing is also shown in the. You belong to which batch? Practical
Uh,
section.
Tuesday, sir.
So this Tuesday things will become a little more clear. So we have
Okay,
a tool that we'll be using. So things will become a little more clear on Tuesday's lab.
okay, thanks. I forgot about that forwarding. Okay,
Okay.
fine. Got
We
it.
can just go through that lectures. I think we'll be
Yes,
able to
yes.
do that. Yeah. Thank you.